In the last video, we began to explore Stokes' theorem. And what I want to do in this video is to see whether it's consistent with some of what we have already seen. And to do that, let's imagine. So let me draw my axes. So that's my z-axis. That is my x-axis. And then that is my y-axis. And now let's imagine a region in the xy plane. So let me draw it like this. So let's say this is my region in the xy plane. I will call that region R. And I also have a boundary of that region. And let's say we care about the direction that we traverse the boundary. And let's say we're going to traverse it in a counterclockwise direction. So we have this path that goes around this region. We can call that C. So we'll call that C, and we're going to traverse it in the counterclockwise direction. And let's say that we also have a vector field. We also have a vector field f that essentially its I component is just going to be a function of x and y. And its j component is only going to be a function of x and y. And let's say it has no k component. So the vector field on this region, it might look something like this. I'm just drawing random things. And then if you go off that region, if you go in the z direction, it's just going to look the same as you go higher and higher. So that vector wouldn't change as you change your z component. And all of the vectors would essentially be parallel to, or if z is 0, actually sitting on the xy plane. Now given this, let's think about what Stokes' theorem would tell us about the value of the line integral over the contour. Let me draw that a little bit neater. The line integral over the contour C of f dot dr. F dot lowercase dr, where dr is obviously going along the contour. So if we take Stokes' theorem, then this quantity right over here should be equal to this quantity right over here. It should be equal to the double integral over the surface. Well, this region is really just a surface that's sitting in the xy plane. So it should really just be the double integral. Let me write that in that same. It'll be the double integral over our region, which is really just the same thing as our surface, of the curl of f dot n. So let's just think about what the curl of f dot n is. And then ds would just be a little chunk of our region, a little chunk of our flattened surface right over there. So instead of ds, I'll just write dA. I'll just write dA there. But let's think about what curl of f dot n would actually be. So let's work on curl of f first. So the curl of f, and the way I always remember it is we're going to take the determinant of this I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. This is just the definition of taking the curl. We're figuring out how much this vector field is would cause something to spin. And then we want the I component, which is our function p, which is just a function of x and y. J component, which is just the function q, and there was no z component over here. So 0. And so this is going to be equal to, well, if we look at the I component, it's going to be the partial of y of 0. That's just going to be 0, minus the partial of q with respect to z. Well, what's the partial of q with respect to z? Well, q isn't a function of z at all, so that's also going to be 0. Let me write this out just so it's not too confusing. So our I component is going to be partial of 0 with respect to y. Well, that's just going to be 0, minus the partial of q with respect to z. Well, the partial of q with respect to z is just going to be 0. So we have a 0 I component, and then we want to subtract the j component. And then the j component, partial of 0 with respect to x is 0. And then from that, you're going to subtract the partial of p with respect to z. Well, once again, p is not a function of z at all. So that's going to be 0 again. And then you have plus k times the partial of q with respect to x. Remember, this is just the partial derivative operator. So partial of q with respect to x, partial of q with respect to x. And from that, we're going to subtract the partial of p with respect to y. The partial of p with respect to y. So the curl of f just simplifies to this right over here. Now, what is n. What is the unit normal vector? Well, we're in the xy plane, so the unit normal vector is just going to be straight up in the z direction. It's going to have a magnitude of 1. So in this case, our unit normal vector is just going to be the k vector. So we're essentially just going to take, so curl of f is this, and our unit normal vector is just going to be equal to the k is just going to be the k unit vector. It's going to go straight up. So what happens if we take the curl of f dot k? If we just dot this with k, we're just dotting this with this. Well, we're just going to end up with this part right over here. So curl of f dot the unit normal vector is just going to be equal to this business. It's just going to be equal to the partial of q with respect to x minus the partial of p with respect to y. And this is neat, because using Stokes' theorem in this special case where we're dealing with a flattened out surface in the xy plane, in this situation, this just boiled down to Green's theorem. This thing right over here just boiled down to Green's theorem. So we see that Green's theorem is really just a special case. Let me write theorem a little bit neater. We see that Green's theorem is really just a special case of Stokes' theorem, where our surface is flattened out and it's in the xy plane. So that should make us feel pretty good, although we still have not proven Stokes' theorem. But the one thing that I do like about this is seeing that Green's theorem and Stokes' theorem is consistent, is now it starts to make sense of this right over here. When we first learned Green's theorem, we're like, what is this? What's going on over here? But now this is telling us this is just taking the curl in this region along this surface. And now it starts to make a lot of sense based on the intuition that we saw in the last video.